All right, welcome and good evening. We are picking up from our session last week. And last week, we were looking at hypothesis testing right here in econometrics, how that is basically applied. And we did so by looking at, let me just take you to what we were doing last week. We basically did that by at least going through this example here, which was from June 2023, how to basically test for significance using the 5% hypothesis. So what we did here was, first of all, locating the critical value, how to get the critical value, which we're going to use to measure against our t values that we get by dividing this amount here, which is the coefficient, by these ones here, the ones that you find at the bottom, which are the standard errors. So you divide those two, you'd basically get the t values, and then you can compare the t value against the critical value to decide whether or not you accept or reject. So if you didn't get that part, just go through the previous session, because this is definitely going to come. And most of these questions carry not less than 10 marks. So they are very crucial for our understanding. So still in line with this year, today, we are building up, looking at specifications, particularly going to be looking at specification problems, which are specification errors, right? What happens with specification errors, and how can you deal with those there? So what you do, of course, when we talk of specifying an econometric equation, we are looking at three parts here. Let me just zoom this here so that we don't miss anything. So I'll be picking important stuff from the textbook and then leaving out what I think is not really that necessary. So when we talk of specification in terms of an econometric equation, we are looking at three things basically, which is, number one, choosing the correct independent variables, and then the correct functional form, and then again choosing the correct stochastic error term. So what do we mean by these terms here? So remember, you are a researcher in this context, right? You are a researcher, and we did say in our introduction that in terms of our regression model, you are basically looking at or looking for independent variables, which are variables that have got an effect on a dependent variable. That's what you are basically looking for there. So you basically have two things, two elements that you have, economic elements that you are dealing with. Let's just say for a simple model, you've got two elements. So first of all, there is one that you want to predict, and then the other one is the predict, right? So which means what you have at the beginning of the research problem, or at the beginning of your research, is the dependent variable, which is the one that you are trying to estimate. And then your job from there now would be to look for independent variables, which are variables that you believe have got an effect on that dependent variable, right? So that's part of what you are doing when you are specifying the econometric equation. That's what you are basically doing. And then from then on, you also want to choose the functional form. So in terms of functional forms, there are many functional forms that you can come up with, most of which, the one that we mostly use could be the linear one, right? But there are instances where it can be polynomial. Sometimes it can be, different kinds. It can be logarithms, sometimes it's just a lot, it's just many that you can get from there, right? So when we're describing that, we are basically describing the functional form. So the importance of the functional form is it also specifies the kind of relationship that your dependent variable has with your independent variable. So in other words, you find there is a change. Suppose you've chosen the right independent variable. So we are agreeing that there is a change whenever, there is a change in your dependent variable whenever there's a slight change in your independent variables. But how the change goes then basically depends on the functional form of your econometric equation, right? So specification error, therefore, is when any one of these choices made is incorrect. So when you make a mistake on any one of those, we refer to that there as a specification error, right? So let's have a look at that slightly in detail, right? Sometimes a specification error can result from omitted variables, right? An omitted variable. So initially we're saying you want to pick all the variables that you think have got an effect on the dependent variable. You basically want to gather them all, put them all in the equation, right? As long as, of course, they are not repeated variables, but we are going to deal with that one a little bit later. Suppose you've omitted a variable. What's the effect of that? All right. So which is basically forgetting to include one. Sometimes it's because you don't even know, right? Our knowledge is incorrect. So the result of both these situations is an omitted variable, right? Whatever the case is, say you forget to include a relevant variable, or you don't get data for that relevant variable. So the effect of that is what we call an omitted variable, which is basically leaving out a variable. So which is defined as an important explanatory variable that has been left out of the regression model. So when we talk of an omitted variable, remember that we are dealing with a variable that is important, which is relevant, right? So it's not just any variable that has been omitted, but a relevant variable that has been omitted. So leaving out a relevant variable like the price, say, from the demand equation, not only prevents you from getting an estimate of the coefficient of price, but also usually causes bias in the estimated coefficients of variables. So what we mean now by this, so except the fact that you have left it out and you don't have a coefficient. So a coefficient, say you've left out the price here, it means that you don't have now the coefficient of price, right? You don't have that coefficient, which will basically make use of this thing to try and make predictions, right? Predictions. So which means you have basically disadvantaged yourself in that regard because you don't have the coefficient. You have not captured now the changes between price and demand. That has not been captured explicitly, right? But it also causes bias, right? The bias caused by leaving a variable output, sorry, a variable out, by leaving a variable out of an equation is called omitted variable bias. So that's the term that is used for that there. All right, so let's look at what effect bias has, right? Which is basically the consequences of omitting that there. So suppose this is what the equation is supposed to look like. So we would say this is the true relationship, right? The true regression model. This is how it's supposed to look like. Let's say you've got independent variable 1 and independent variable 2. This here is the stochastic error, and by definition, we're saying the stochastic error basically captures all those variations, right, or all those changes in y, which cannot be explained by or the x's that should be included there. So if there's any other change that occurs, it's going to be captured on the stochastic error. And we're saying by definition it has to be random, right? It has to be an erratic change, right? It cannot be predictable. It's not something that you can predict, assuming that you have exhausted all your knowledge there. So which means all that comes here is something that is beyond your knowledge. So suppose now, for some reason, you've omitted, like in the example here, you've omitted this one here, the second independent variable, x2. What's going to happen? Our stochastic error is not going to be the same as that one because there are going to be variations now, right? There are going to be variations in y which cannot be explained by x, and some of those variations are variations in that other x which you have omitted. So which means that other x is now going to be captured where as a stochastic error. So which means the stochastic error now is going to include this here, right? So the stochastic error term includes the effects of any omitted variable, right? In this instance now, which is quite by accident. So your stochastic error is not really supposed to include that, but because there are variations in the equations which you cannot explain, those variations are going to fall under stochastic error. So that's the effect there. Note again, this here is also not going to be the same, obviously. If you remember well, in our assignment 1, when we were running those regression models, I think the first one that we ran was a single variate equation. It was a simple equation. It only had one independent variable, right? So you realize that when we ran it the second time, we can add that independent variable. The constant term was not the same. Right? The constant term was not the same. So which means adding and subtracting or omitting a variable also has an effect on the constant term, which basically reflects where the graph cuts your y-axis there, which is your constant term. So it's not going to be the same, and then your stochastic error again is not going to be the same. Right? But let's have a look at bias, right, in terms of numbers, where bias is going to come in there. I want to look for a real example. All right, let's see. So suppose you have run this, and this is what it looks like. Similar to what we did in the assignment. We have ran this, and then this is what you get there. So the effects now of these things, why we basically make use of, I'm just going to interpret these findings here. Just a second. So I want to hang this up. All right, I just want to hang this one up. All right. Sorry about that. All right, so this is what we pretty much got there when we ran the equation, right? And then you can see where this comes in, right? This is used in calculating our t-values, which is what we're covering in the previous class. And where we are taking, we say it is the standard errors, right? Making use of these standard errors. And then, so we're dividing the coefficient by the standard errors to arrive at these values here. So these values are basically used and measured against the critical value to decide how significant, how statistically significant these coefficients are. Right? So when we talk of statistical significance, we're saying how different is it from zero? Right? Is it significantly different or insignificantly different? So if you remember, in most instances when we're doing, say, I think on the last example, based on the question that was asked, we dealt with a situation where we were dealing with a two-way test, right? We're dealing with a two-way test where we're saying that one works in circumstances where you don't exactly know the sign, right? You don't have an expectation in terms of the signs. So in other words, you're saying the relationship can be positive and it can be negative, you just don't know. So in running the significance test, we therefore run it in terms of it could go either way. So if it could go either way, then which means our null hypothesis then should have been not equal to, right? Or excuse me, our null hypothesis should have been equal to 0, right? And then the other one, the alternative, should have therefore been, could have been not 0, anything that's not 0, so it could be negative or positive. That's the alternative. So in terms of the first one, which is the null hypothesis, where we are saying it's not equal to 0, right? Also is equal to 0. I wish I wrote this down somewhere. So where we are saying the null hypothesis, where we are saying is equal to 0. So by definition, we're saying, or in principle, we're saying the null hypothesis, we are basically telling ourselves that it's what we don't expect. So when we're saying the coefficient is equal to 0, it simply means that there is no relationship between those two. So remember, we're saying if it's 0, it means that there is absolutely no relationship. It's going to be represented by a straight line if you're going to put it on the Cartesian plane. So which is what we do not expect there. Right. So we run the tests, right? We therefore run the tests based on that. So which means we're saying what you don't expect, even in dealing with a single-sided test, there is still that portion where we are saying it could be less than or equal to 0 or greater than or equal to 0. So that possibility that it's not what we think it is. So it means there is a likelihood that it could even be 0, meaning that there could be no relationship at all. For instance, price does not affect demand, right? So in that instance, the coefficient of price would be 0, right? When we are saying that it does not affect demand. So in that regression, that coefficient is going to be 0. So when we are doing these tests now, because this is more of intelligent guessing now, we are saying how significant is it now in terms of how significantly different is it from 0, right? Or in other words, how significantly different is it from what we don't want it to be, or from what we don't expect it to be, right? So which means we want it to be significantly bigger than the critical value, right? Which is convincing. So it's like passing an exam. You could pass an exam with 55%. It is a pass, but it's not a significant pass, right? It's not really a significant pass. But once you are in your 80s and your 100, you are saying you are significantly different, right? You are significantly different. So it's a significant pass there. So that's what we'll be dealing with in those when we're calculating these t values. And then of course n is just the number of observations there, and then your adjusted R-squared, this one we've also covered, right, which is our coefficient of determination. So this one basically tells us how much, or gives us the percentage of how much is explained, right? How much is explained by our model in terms of the data that's given, how much of that data does our model explain, right? So you obviously want that to be higher now. So back to what we're dealing with now in terms of omitted variables. Suppose now, like in this instance, they've omitted this one, price, right? You can see here that, for instance, the constant term has changed, right? Then not only has the constant term changed, but if you look at here, if you look at this part here, this 9075 has shifted now, it has changed to 1487, right? And then this I here is increased to 2.3222. So this is what we refer to as bias. This is what we refer to as bias, where if you're omitting an important variable, it's going to affect the coefficients of all these other variables. So that's what we refer to as bias there. That's one way you can check that. And then again, if you look at your adjusted R-squared, it was 0.579 in terms of our overall fit. We said it measures overall fit, right, of the regression model. Now it has gone down to 0.25. So it's an indication that the variable that was omitted is an important and is a relevant variable. So that's a very big sign there of bias. So that's how bias is detected there. So if you do the same for if you do the same, let's say if you remove a variable, an independent variable that is not significant, or that is not relevant, right? What would happen is the changes are going to be slight. For instance, your adjusted R-squared is not going to change significantly, and then the coefficients of these other ones are also not going to change significantly. Right. So to sum, if a relevant variable is left out of the regression equation, there is no longer an estimate of the coefficient of the variable in the equation. What we said, if you leave out price, then there's no longer that estimate, and then the coefficients of the remaining variables are likely to be biased. So which is what we're looking at there. So if they are biased, then they are basically going to give you, if you're using this to make predictions, they are basically going to give you incorrect predictions, right? So let's say we said some of the uses of this regression model is to help you in making decisions, say in a company. When I say by how much should we increase our advertising costs for us to achieve a certain level of sales? You see. So if your coefficients are not correct now as a result of an omitted variable, then you are going to miss it in terms of your predictions. You are obviously going to miss it. So how do you correct that? In theory, the solution is just to include the omitted variable, right? Though in practice, it's a lot more difficult, right? Why? Because an omitted variable is very hard to detect. Why is it hard to detect? Normally, it's because you wouldn't really omit a variable deliberately. It's most likely because you do not know, right? It's most likely because you do not know that. So it's going to be very difficult for you to. Sometimes these things are not even easy to detect because sometimes the bias is too small, right? For you to even detect that, right? And then, of course, the other problem is choosing which variable to add to the equation once you've decided that it is suffering from a variable bias, right? So which one are you therefore going to add? So it's a lot more complicated in practice than here in theory. So in theory, you simply need to add the one that is omitted, right? So once you add the variable, then you want to check the adjusted R-squared, the coefficient of determination adjusted for degrees of freedom, to see if there is a change in that. So if it increases, it means there is merit in adding that independent variable. If it doesn't increase, you might as well have added a useless variable, which is the ones that we are doing now, irrelevant variable. So yeah,
Sorry to interrupt.
yes,
Okay, you say in practical, it's difficult to pick up the omitted variable.
yes,
So in theory, is it given to
yeah.
make it easier for you to be able to?
In theory, they'll probably give you something like this here, like what we're dealing with here. In theory, you basically look at this here, the adjusted R-squared, and see if there is a change in the adjusted R-squared. Then if they don't give you something like this, they would have given you things that you probably have covered in your economics. For instance, if you look at demand, you probably have an idea of how many other things affect demand. You see, the demand of a product or of a certain commodity. For instance, they could be, maybe let's just say the equation only has income and it only has the price of the product as those two explanatory variables. So there's a likelihood that you've not included things like substitute product, the price of the substitute, and the price of related commodities. You have not included all those things, all those other things that might have an effect on that. So they will not give you something very complicated, something that is far from what you know. It would be basic. And then again, because they are not really testing new economics, most of it will be in terms of how how are you able to detect this bias, right? How are you able to detect this bias? You can see that here, even on this example, they are simply putting N's and P's and I's, right? But we are assuming that if you are going to be doing this in practice, then you would have read in detail about those things of which you don't really have time for that. So they are testing you econometrics. So what's in econometrics? Then you are dealing with bias and then how to detect bias. So you want to detect it, like we said, on the adjusted R-squared. This one is easier to check out. And then you also want to check out on the changes there, right? The changes. Then again, maybe if you look at this one here, another thing I believe I see it's being mentioned here. If you look at the change on the T-score here, right? It was 4.42. Now it has gone down to 0.84. So which means your conclusion now is this one here is insignificant, right? This one is insignificantly different from zero now. So which means you are now basically going to have to disregard this this coefficient here, because it's not exactly different from 0, right? So you fail to reject the null hypothesis in these circumstances merely because you've omitted one variable. Look at the effect of that. You see, it's even really affecting many other variables there. You see, and then this one here, the t-value has gone up. This one here, it has gone down, but the overall fit has gone down. See? So it's just messed up now. So that's what we are basically dealing with in econometrics. So if they ask you, how do you correct that? Most of our questions here in econometrics is, how do you correct this situation? Then you simply add the omitted variable, right? And then see if that affects the adjusted R squared to show that there is merit in your inclusion of that omitted variable. All right, so, but what happens now, say, if you're including an irrelevant variable, right? So irrelevant variable is the converse of omitted variables and can be analyzed using the model. Let's see, 6.1, right? So this is what you have. Suppose now you've put in an extra one, right? You've put in an extra one. So you can see now the difference between that. The one that we had on top, it was the stochastic error plus. Now it's the stochastic error minus. Right? So as a result of our wrongly specifying that, so we have something totally different now. So such a mistake won't cause bias, right? How so? Right? This is in the instance where this beta coefficient is equal to 0. So in other words, it's irrelevant. It's an irrelevant variable. It does not affect your y. So it's not going to cause bias on these ones here. So how are we first going to detect that your adjusted R squared is not going to be affected much, right, in terms of its inclusion, but instead it's going to go down to indicate that there is no merit, right? There is no merit in the inclusion of in the inclusion of that variable, right? Even though your R squared might go up, right? Because your R squared, remember, it normally goes up whenever you put in an extra independent variable, but your adjusted R squared, it checks for merit, right? So it's going to decrease, fine. Usually it is going to decrease just because you've added something that is irrelevant. So it's behaving opposite to what was happening there on the first instance. So in the first instance, when we omitted a variable, it decreased, right, as a result of the omission. Then once you re-add it, it's going to increase, right, go back to normal. But in this instance, you've included something that's not supposed to be included, so the overall fit goes down. Then once you remove it, the overall fit is going to go up. So obviously the solution to this would be to remove it, right, because it's not supposed to be there. So although the irrelevant variable causes no bias, it causes problems of regression because it reduces the t-scores and the R squared. So your R squared, your adjusted R squared, remember, it measures the quality of your fit, right? So which means you don't want an equation that's a poor fit. You really don't want that thing. But let's just see how it does not cause bias, right? Let's just have a look at that. So this is what we have now initially, I believe, and then they decide to add the last one, which is that A there, right? So our adjusted R squared is 0. So how you check if A is relevant or irrelevant, we look at the adjusted R squared. So it was 0.579. Now it has gone down to 0.569. It's not a big drop, yes, but it's an indication that you've included something that is not relevant. So instead of going up, it has gone down. Let's look at the values themselves. So this is 8975. This one is 9079. There's no much of a difference in these numbers. 0.354, 0.60. So in terms of making predictions, we don't really expect in any case that this is going to give you predictions that are 100% accurate, because we are dealing with samples, etc. and there is the stochastic error involved anyway. So we don't really expect to get 100%. So anything that is pretty
Okay,
close
I
there,
have load. Sorry about that. I have load shedding now.
oh, you're going to get cut off. All right,
But
no,
you
it's
can
fine.
carry on.
Since there's, but I'm almost done anyway. I'm almost done. I'm just gonna finish this part and then we'll pick it up on the next session. All right, so because these are not significantly different from each other, it means there is no bias there. If you look at that there isn't any bias. But let's look at the change in terms of the t values. So our t value is 4.31. There it's 4.42, 4.48, 4.86. Right, let's look at the comment on that there in our conclusion. Finally, the t-score for the potential variable A is small, indicating that it is not significantly different. So particularly these ones are fine, right? These ones are okay. Just because there is no bias, they still remain high, right? Meaning that we are rejecting the null hypothesis, right? They are statistically different. They are far away from the critical value. But this one here is 0.69. It's almost zero. So it's very small, right? So which means it's statistically insignificant. So there's no much merit in including that there. All right, so we'll end with this one here, right? 4 important specification criteria. Number 1, theory. Is the variables placed in the equation unambiguous and theoretically sound? Right, and then you also want to do, so theory, obviously, you want to check if it conforms with theory, right? With the relevant theory that we know regarding the subject matter. And then the t-test, again, significant in the expected direction. Is the variable's estimated coefficient significant in the expected direction? So it's those two issues there. Is it big enough and is it in the expected direction? You see. So this one here, that was useless. Fine, it's in the right direction, but it's not big enough, so it's not significant. So it would have failed the t-test. Maybe it could pass the theory, but failed the t-test. And then we look at the adjusted R-squared the way we are saying. So does the overall fit of the equation improve when a variable is added? And then do other variables' coefficient change significantly when the variable is added? That's what we basically look at there. All right, I think we can end the session here, and then we'll meet on our next one.